Hello, everyone. Thanks for joining that new session. We continue the topic of metallurgy with this talk from Sami Elzabag from GMH company in Germany. Please let me first introduce Sami to you. Sami is engineer at Georgsmarienhütte company in Germany. He holds a degree in production engineering since 2000 and in metallurgical engineering since 2004. His PhD thesis in the field of electric steelmaking is accepted by the Aachen University, and publication is currently in progress, actually. Working experience, after 2 years blast furnace experience, he joined GMH in 2006 as a process metallurgist for steel making. He has experience in data analytics and since November 2017 performing solidification simulation using THERCAST application. His talk today is titled Optimal Design of a New Ingot Casting Format by Combining the Power of Numerical Simulation and Surrogate-Based Optimization. With this said, off to you, Sami, and the ground is yours.
Thank you a lot, Laurent, for your introduction, and hello, everybody. I will try now to share my screen. Can everyone see my screen?
Yes, we can see it.
Yeah, fine. Yeah, thank you for the introduction of the topic. Who are we? We are a steel-making plant. Not only a steel-making plant, but we are a big group with a lot of business units, producing business units. We are 100% privately managed, working internationally, more than 50 countries. Due to the 100% use of steel scrap in the electric arc furnace, we have a low carbon footprint in our steel production. With 6,000 employees, we have a 2 billion euros turnaround. We are a producer of engineering steel and special profiles, and we produce also heavy components, which are castings or forgings. And as well as we are specialists for processing specialty scraps for steel recycling. The markets where we are active are in mainly in automotive, energy, transport, logistics, railway, consumer goods, and food industry. Like the label of Intel inside on your computer, you should say on 4 or 5 cores you can have the label GMH inside. 4 or 5 cores contain steel made by GMH Gruppe. We are located, as you, Laurent, introduced, located in Germany by Osnabrück as a steel maker. And we are also located, these are our locations worldwide. In our process locally at Georgsmarienhütte GmbH or GMH, we produce our steel by recycling steel scrap into electric arc furnace. The liquid, after the secondary metallurgical treatment of the liquid steel, we produce cast billets and as cast ingots, which are partially going, of course, to the customers for processing, but also we produce steel bars in our rolling mill, which are either as rolled or heat treated or as bright bars. Our focus today is the ingot casting of steel, where we have to propose a new ingot design for our customer and propose a feasible geometry respecting the process itself and the customer's requirements and constraints. We want to create a healthy part and high metallic yield, avoid and minimize, that is the very important thing, try and error on the real product itself. So we want to do a digital optimization with numerical simulation. Using THERCAST, we can produce or we can model and do forecast or prediction of the shrinkage behavior of the solidified part. as well as model the centerline porosity. Other attributes which we can model or simulate with THERCAST are segregation, ghost lines, hot tearing. But the point is that that is all fine. But which attributes or process parameters in the design space impact these results? And that is actually the point which we are talking about. If we have such a simulated part, what is the design space to be investigated? The ingot dimensions. Given a constant mass, we speak about 5 tons, 10 tons, 30, 40, whatever tons. You have a variation in the if you vary the dimensions, you vary what is the behavior of or the influence of height cross-sectional ratio, conicity of the geometry of the mold, the riser dimensions, the insulation dimensions, as well as their thermal properties, given process data like the steel grade, the mass flow rate during pouring, superheat, and so on. That's all nice. What we do is just what you see, the colored photo in front of you is just a single combination of the of one single configuration of the geometry, process parameter, thermal properties, and boundary conditions. So we want to explore the design space and optimize this process. How to do this? If we talk about design of experiments, we talk about two-stage full factorial design. Two-stage means that every parameter, low value, high value. What happens if I investigate 2 parameters? I have 4 virtual experiments. If I have 4, I have 16 and so experiment and so on. So it's getting too much. The previously mentioned parameters, we are talking about more than 16,000 simulations to be done to investigate this design space just like this. And when we talk about processes which are not linear, with a non-linear behavior, with minima, maxima, asymptotic behaviors, how the parameters are interacting together, then we are talking about billions of probabilities or to be investigated. So that's what we did with together with Data Advance and GMH, to use P7 as the mind of the whole workflow. We have the Inventor for CAD and THERCAST for the meshing setup and the real numerical computation itself. We consider this as a black box, and P7 does the design space exploration, gives the parameters, do the control and the triggering of all of the workflow, and gathers the responses at the end of each simulation, all in an automated closed loop. And it is done like this, that we have variables and responses. Variables like riser geometry, insulation attributes, and other geometrical attributes and other process data, whatever, how are they can be hundreds, but you have to define them. You have lower bound, you have an upper, you can define the bounds, the levels, if in case of categorical variables, and then afterwards gather and then send this configuration to the black box, the before mentioned black box. Then you get, after from this black box, you gather the responses to like porosity attributes, metal loss, and so on. And that is in detail looks like this. If I look into the black box, then we submit the input, the design variables, the CAD is going to be triggered, the geometry is going to be produced, the meshing, the parametrization, the solidification, simulation, and afterwards the parameter documentation, data acquisition, analysis, and these responses are gathered from the black box back to the design space exploration of P7 for deciding for the next iteration. And what the nice thing on hand, these are 350 simulations done by in this workflow, and we have the possibility to explore the results of this investigated time space, design space. We have the parameters which we vary, we have the responses which we gather, and we can have a look and understand what happens, how our bad results, or in terms of porosity or health of the product, or information in terms of good. And we see that we have the possibility also in our optimization to find good porosity and also optimize the metallic yield, and understand which parameters are relevant, and understand how they interact together, and which parameters are not really so relevant, whatever we do the variation. So that is also an important thing for us to understand as engineer. I make hundreds of simulations, how to understand what I did at the end, all at one glance. Other possibilities which we of course get and use from P7 is to analyze the dependencies and the correlation and of the feature importance. Is the feature investigated? Is it really important, or we can just neglect it? And understand the dependencies, how they correlate together, and go further and have an understanding and have a feeling for what I am designing. And then we get to the next step, and which is more or less the final one, to get to the surrogate-based optimization. And then instead of just evaluating the responses, we say we want to minimize the porosity attributes, the metal loss, whatever criteria we have, and get our final design. So concluding, we have, using a numerical simulation, we can predict the solidification and the quality of the ingot. Using P7 for design space exploration and optimization, we can automatically trigger the workflow in a closed loop and save human time and idle times of the server. It means it runs 24/7. Understand the relevance and the interactions of the parameter. We did an optimization with 350 computation, and can gain an understanding and get an optimization in less than 3 weeks. And when we combine the power of numerical simulation and surrogate-based optimization, we have a deep understanding of the process and development of products with optimized qualities and costs in record time. That's it. Thank you a lot for your kind attention. I'm ready for your questions.
Thanks a lot for this presentation. So let's switch to the first question. In your presentation, you use the CAD Inventor.
Yes.
But how easily could you use another CAD tool?
It is a matter of how the CAD tool. It is a matter of it is a licensing. So it doesn't matter if you're talking about CATIA, you are talking about Inventor, and so on. We are not the only people. We have a simulation team. We are not the only people using CAD. There are other departments using CAD. So that is a point to say, okay, where this is a thing which you have to decide as a company. If you say you have a big team and the most people are using Inventor, then you have to orient to Inventor. And if the main philosophy to say let's work all with CATIA, then it was the point: which resources do I have? Can I get them? What is better for all? That is, I took Inventor because it was there, it was available, and it also, if you are talking with construction departments who are not doing simulation but doing construction and so it makes the data exchange easier. So
Okay.
I did it because it was there.
Okay. It means that if you add another tool, it's easy to replace it
Yeah.
within P7. Okay.
Yeah.
But it's what blog, sorry, did you use to run THERCAST? Is it running locally or remotely?
That is the point. You have to run the THERCAST. You have certain command files which you have to trigger, and either you say you have it local on your working PC. You let your working PC 24/7 running and do it, or you have somewhere a cluster or a cloud, and you have a connection, and then you have to trigger. That is the point of the communication. So it is a point that we compute on high performance clusters, and so we have to manage the data flow and the communication via our company network. So that is either, if you say on your locally or server, that you have to manage the communication.
Okay, thank you. And a final one, which is, what tools did you use for pre and post processing? How did you automate the extraction of the physical criteria of the center of the ingot?
That is a matter of the details. You have that is a matter of details when you work with a simulation. You have virtual sensors, and the point is how to extract the information from virtual sensors. There are a lot of possibilities, but that is the point. We have to acquire the information from these sensors, and the nodal information, and position the sensors on the relevant area. And you must, as a simulation engineer, one must look how the data is, the generated data is saved on the in the whole workflow, and then read it. And that is the, let me say, in German you would say, devil lies in the details. That is the point. What is in our specific case, we have to know where are the data saved, how are they saved, and how to access them.
Okay, thanks a lot, Sami. I don't see any new question. So it's time to switch to next session, and speak to you soon. Thank you again.
See you. Bye bye.
Bye for now.
Bye bye.